Hi, welcome to the 87th Cold Spring Harbor Symposium. I'm Jan Witkowski and I work here at Cold Spring Harbor. The subject of the symposium this year is stem cells, and I'm very pleased to have Leonard Zon here from Harvard. And Leonard, your lab's focus or broad area of interest is hematopoiesis.
Yeah, we've been studying blood development for a long time, and we've used the zebrafish as a model system to study blood development. Zebrafish are transparent, so you can see all the organs under a light microscope, and we can see the blood cells whipping through the circulation, and it's a wonderful system to study. Each mother has 300 babies a week, so we say daycare is very expensive for the zebrafish, and we've been making mutant fish that can't make blood and studying them, and then over the past 10 or 15 years studying blood stem cells in particular, and so that's our major focus of the lab.
And what sort of tools and techniques do you use?
Yeah, so lately we've been using something called cellular barcoding, and this is a relatively new technique, and we are able to do it in a variety of different ways. So one is using DNA as a barcode, and so we have one way is to color every single stem cell a different color. And we do this with a certain plasmid, and we induce recombination of this plasmid that has red, blue, and green. And it can dial up all the colors of the spectrum. So similar to the old RGB TV sets, you can get the entire color of the spectrum. So one of the tricks that we do is to color all of the embryonic blood in different shades and hues, and then all the stem cells have a different color. And we grow the animal up to adulthood. All of the embryonic blood dies off, but the stem cells are each colored. And then you can follow clones of stem cells then that have been born during embryogenesis and have persisted to adulthood. And that turns out to be unbelievably invaluable. And we've been able to bleed the animals monthly and follow clones of stem cells, and we've been able to sort when a clone becomes dominant as a result of a mutation or a disease on the way perhaps to leukemia. We get a dominant color, and we can sort that dominant color and study it really easily, and so that's been a fantastic system for us.
You said mutations rise. Are these just sort of spontaneous, naturally occurring, or do you induce mutations?
Yeah.
Or what?
So what we've done, we recently had a paper where in humans, as we age, surprisingly, we develop mutations in stem cells, and this makes a stem cell become dominant in the bone marrow, and that predisposes old people to becoming what's called myelodysplasia, a pre-leukemic state, or ultimately getting leukemia. And this is incredibly common. It's 17% of all 70-year-olds, 30% of all 80-year-olds, and 50% of all 90-year-olds have mutations in their blood cells that are causing these dominant clones. And all of these are in about 20 different genes. And a lot of these are epigenetic regulators. They're not working, they're turning on certain genes and turning off certain programs. And so the mechanism by which this whole clonal hematopoiesis has happened has not been found, but what we were able to find is that in these dominant clones, the mutant cells that are made from these clones, macrophages and neutrophils, are pumping out inflammatory cytokines. And that causes the whole marrow to be inflamed, and then the stem cells are making anti-inflammatory factors, so they become resistant to the to the inflammation, and then you end up getting clones that become dominant over time as a result.
Right, so let me get that right. So there are mutations occurring in the stem cells.
Yes.
The stem cells may become clonally dominant, and they give rise to the other cell lineages like macrophages.
Exactly.
And they start pumping out cytokines and causing inflammation.
Yeah.
But the original mutant stem cells can become resistant to the inflammation.
Exactly. And so what we were able to do is we were able to knock out a pathway that is anti-inflammatory in the stem cells, and that restored the balance to the marrow. And we actually have a small molecule now that hits this one pathway, and we would think that this might actually restore balance to people who have this particular disorder.
So is this disorder, this inflammatory response, is that on the pathway to full-blown leukemia?
Yeah, it is. So, well, the original mutation, which is in a few different epigenetic regulators, that's on the way to the mutation. The anti-inflammatory pathway has nothing to do with that, but is just a pathway that seems to be induced, and it's turned up, and it's creating these stem cells that are resistant to the inflammation, so they have a chance of being selected and continue.
There's always a discussion about how true models are to the human condition.
Yeah.
And I in my prejudices, I would have thought fish was further away than a mouse, for example. Does the zebrafish system recapitulate fairly accurately what's known about the human?
For blood diseases, it certainly does. I mean, we've in our original sets of experiments years ago, we made mutant fish that had no blood or had decreased blood cells, and then we discovered a few genes that was causing this, and then we found humans who were mutated in the same genes who had anemia. And so there's a very strong correlation. So most of what we found in the fish has applied to the humans. There's certainly differences. The fish is a small little animal, doesn't quite have as many blood stem cells as you and I, but overall the general principles are there.
And you said you made fish without blood. They're presumably not very happy.
Yeah, so it turns out in fish you don't need blood for the first 5 days of development. And so you can actually carbon monoxide treat a fish and it's totally fine. It'll absorb enough oxygen through its skin to be able to survive. After 5 days, it's in trouble. Those fish that that have no blood, in general, they'll expire, they'll die. But occasionally a new source of stem cells comes up and they'll live. So we have some fish that are bloodless and they have no blood, but then all of a sudden they start making some new blood. And so it's again a question of new stem cell sources that come up that are very interesting.
So sticking with that for a moment, do you know where these stem cells come from in these bloodless fish?
We don't know. It's a really good question, and I just went to a poster here, and there's a very young, talented woman in Teresa Bowman's lab trying to work on this, and that sounds very interesting. So they don't know yet either, but I think that if we could trace it down, it might give us from a therapeutic standpoint to try to understand the diversity of stem cells that can function in an animal.
Right. Because by the bone marrow stem cells are no longer, certainly not totipotent,
right?
But are they multipotent?
Multipotent.
Oh, well,
yes.
they are, because they give rise to
they
these
give rise
various
to
cell
red
lineages.
cells, platelets, and T cells and things like that. So yeah.
But they wouldn't become a myogenic stem cell.
No. You can obviously take a blood cell. We do this all the time in our stem cell program at Boston Children's Hospital. You can take a blood cell and reprogram it back to becoming a stem cell line, an iPS cell line, and a pluripotent cell. And so there is some, if you are willing to put transcription factors in to reprogram cells, you could actually turn it back for sure.
Yeah. So it's a bit off your specific topic, but in that you always have to go back. You can't take a differentiated cell and go straight to some other differentiated. You have to come back to the.
Well, I think that's true for iPS cell generation, but there are some certain cases of going straight to the lineage. And I think some of these are very interesting. In the hematopoietic system, there's some really interesting examples of having a B cell go straight to a myeloid cell. And doesn't go back to the stem cell and back so it basically just goes straight. And these are through some transcription factor reprogramming and the work of Thomas Graf. So it does happen that you can transit.
I was thinking of Conrad Waddington's epigenetic
landscape.
Yes,
you have to. So I think sometimes the hill in the Waddington landscape can be a little shallow, and you can kind of scoot over and get there.
So we must come to a close, but tell me very briefly about the small molecule that you've got, and is it in clinical trial? Or
Not
what
yet.
stage?
We just started. It's a tool compound, and it hits this nuclear hormone receptor that's part of this anti-inflammatory pathway, and we're very excited about that. Yeah, absolutely.
So it's looking promising.
Yeah, well, we've been able to show it in the fish that if you have one of these mutations that leads to this clonal expansion, that one of the mutations that's also true in humans, that this will restore the balance of the marrow, and it will also reduce the level of the mutant clones in the marrow. So we're pretty excited about that.
Well, I think that's just the right high note to end on.
Well, I like ending on a high note. You know, I play the trumpet, and so I always love to end on a high note. That's super good.
Thank you very much, Len.
A pleasure, absolutely.